Greetings, welcome back. In this video, we are extending our conversation of the toy example to linear systems problems that we saw in our last video. Specifically, we start with this matrix vector multiplication problem that has a known output. In the last video, we saw how to use Octave or MATLAB to translate that into the equivalent special form ux equal y using an augmented matrix. We also discussed the idea that once we make that transformation, the solutions that we expect for the original problem are identical to the solution that we expect for the special form problem. Moreover, those solutions come in the template. Complete solutions are always written as a particular solution plus a trivial solution. We spent a lot of time developing the concept that if I want to get any trivial solution, in fact, what I need to do is focus on the non-pivot columns, and for each non-pivot column, generate a unique special trivial solution. Moreover, if we look at the position of these ones, these scalars came from putting a positive 1 in front of the column associated with that non-pivot. That positive 1 is the only non-zero entry in row 2 across these special trivial solutions. Similarly, if I look at the positive 1 in my special trivial solution 2, corresponding to non-pivot column 2, I have a single 1 value across the entire set of vectors. That happens yet in my third and in my fourth. I'm ready to make a conjecture. I conjecture that the reason we call these unique is because these vectors are actually linearly independent from each other. Another way to say that is I cannot generate any of these single vectors as a linear combination of the other vectors in that set. So for example, it is not the case in what I'm seeing that Z4 is some linear combination of the previous Z's. And the reason that that's true is Z4 has a 1 there. If it was a linear combination, I should be able to take some scalar multiples of the previous one and generate that 1. But any scalar multiple of the previous ones will always get sent to 0 in row 7. There's no way to do that. And the same is true because I have all zeros in those rows. I can't get to one of those vectors. That is a classic idea of linear independence. Although the argument I just made was a good hand-waving argument, we do have a formal theoretical structure when we want to prove vectors are linearly independent. Remember that we have a theorem that says that a set of vectors, this is index notation, so z sub k, where k goes from 1 to 4, that's a set containing 4 vectors, z1, z2, z3, and z4. That set is linearly independent if and only if the only linear combination that takes those vectors to 0 is the trivial linear combination, the linear combination with scalars equal to 0. In other words, if I want to prove that this set of vectors is linearly independent, I need to consider any linear combination that gets sent to 0 and show the only way for that to happen is if the individual scalars in that linear combination are exactly equal to 0. All of those scalars should be 0. With this in mind, we can set up our proof. Let's go ahead and take the sum of the z sub k vectors with scalars alpha sub k to match. Those scalars are all real numbers in this case. We know that that's a 4-term sum. On the right-hand side, we have the 0 vector, which is the same size as our original vector. This is not a theoretic exercise. We actually have the individual entries of those, and we notice those 1 values show up in very special places. This is a vector equation. In other words, this is in vector form, but it represents 7 individual scalar equations, which I can write in this form. If I look at each row of that vector equation, I get the corresponding scalar equation. And remember that individual rows connected with individual columns of my coefficient matrix, row 2 had to do with non-pivot column 1 or column 2 of my matrix, and in that row I see 1 times alpha 1 plus 0 equals 0. That immediately implies if I have a linear combination set to 0, I must have that first scalar be equal to 0. The same can be said about conclusions from row 4, 5, and 7. And what that means is the only possible way to take a linear combination of those special solutions, trivial solutions, is to set all of my scalars in that linear combination to 0. That's the definition, or at least the theorem that we used to define linear independence. In other words, indeed, these trivial solutions are unique. They are linearly independent from each other. I cannot generate information encoded in one of those trivial vectors using the other ones. Now let's put a wrap on this problem. Remember from the last video that we actually found exact forms of the vector P and the special trivial solutions for each of the non-pivot columns that composed any trivial solution to the original system. Thus, if I want to write my complete solution, I can do so by adding the particular solution plus any linear combination of the special trivial solutions. The number of special trivial solutions is going to be equal to the number of non-pivot columns. In this case, that's 4. For the specific equation that we have written here, I am writing this in vector form, so I have a vector plus a linear combination of the other vectors. I can also write this in scalar form by just combining the individual scalars along the row, which would produce this vector overall. So if I want to know what these entries need to be, I can choose any values of C1, C2, C3, and C4, and the general solution in terms of scalars will take this form. I've kind of marked it to follow along the same structure. You could, of course, center this if you wanted to make it a little bit more visually appealing. But the claim is all the information encoded in the vector form is the identical information encoded in the scalar form. And this is where I want to push you all in this class a little bit further than most introductory classes will push. This vector sum, where you have a single vector plus a linear combination of other vectors, remember that when I have a linear combination of column vectors, I can write that as a matrix vector product, which means my complete solution is actually an affine transformation of some matrix time a scalar vector. In other words, it's P plus some matrix times a vector C where the scalar coefficients are stored there. Let me repeat that visually. Imagine I take these 4 columns and form a single matrix. We'll call that matrix capital Z. Each column, the first column of Z is the first special trivial solution. The second column of Z is the second special trivial solution. The third and the fourth similarly. The scalars that I can multiply by, which can be anything because a scalar multiple times 0 is still 0, I now store as a 4 by 1 or an F by 1 column vector. And that means my vector equation, where I have a particular solution plus a linear combination of the unique special solutions, actually can be written as a particular solution plus a matrix that sends my original coefficient matrix A to 0, because all of these columns send A to 0, times some scalar coefficients. No matter what scalars I put in, this will always send my coefficient matrix A to 0. So 0 times C is still 0. Again, the columns of that matrix are the special trivial solutions, but this has some real implications. When we started with our matrix equation AX equal B, the general linear systems problem, we translated that general linear systems problem into special form by multiplying on the left-hand side by that sequence of elementary matrices, which here we're going to group together as a single non-singular matrix. We then claimed that the complete solution takes very special form, a particular solution plus any trivial solution, but now we're saying that any trivial solution is going to take the form of a linear combination of special trivial solutions which are linearly independent. We group those together as a single matrix, Z, and then the scaling coefficients can be C. That can be literally any vector. But the point here is when I substitute this value of X into this form or the complete solution template, I can take U times the complete solution template. I can distribute U inside, so this would be U times P plus U times Z times C. That's the form that any trivial solution takes. Notice that u times p is y because p is a particular solution to my original problem. That was the definition of what a particular solution was. U times z is 0, and that 0 has the number of columns of m and the number of non-pivot columns of u. Now this matrix is the 0 matrix. When I multiply the 0 matrix times any vector, I get the 0 vector. And when I add the 0 vector to the original y, I get back to y, which means indeed this vector does solve my problem. But I know more than that. Not only does that vector solve my simplified problem, we claim that it solves the original problem, ax equal b. And the way to see that is, remember that each reduced row echelon matrix comes from multiplying my original coefficients by a non-singular matrix E. Because I know that matrix is non-singular, I can multiply both sides of that equation by the inverse. When I multiply a matrix by its inverse, I get back to the identity matrix on both sides. The identity matrix times any matrix or vector maps back, which means that the particular solution to my transform system is also a particular solution to my original system. Similarly, in the third video in this playlist, we had a theorem that says if I send the matrix U to 0, that is equivalent to sending the matrix A to 0. But I know the matrix Z times C, that sends the matrix U to 0 because the columns of Z come from the individual vectors, which are unique special trivial solutions. The moment I know that that vector sends U to 0, by that theorem, I also know that vector sends A to 0, which means the complete solutions to my original linear systems take the form of a particular solution plus a trivial solution, and the trivial solution is encapsulated in this matrix vector product, which we can look at using those three paradigms, either a vector form of that equation, a linear combination plus some vector p, a scalar form where we go down to the individual scalar entries and look at what that means, or a matrix form where we look at it as some vector plus matrix times vector. And that's what we've done here. That indeed solves our problem. Go ahead and confirm that for yourself. This form is going to show up when we do applications involving electrical circuit analysis, and in particular, in other places in my website, you can take a look at something called the linear algebraic nodal analysis. This is one of the main observations that I contributed to that approach of connecting linear algebraic structures with classic nodal analysis that many engineers would see in their introductory classes. All that is to say, we use this example to develop this structure so that we could use it in practice. In the next video, we're going to state some of the observations that we made in these last two examples formally as a theorem. Then we're going to go on and explore some more. I'll see you there.